I'm going to tell you about object orientation that you can do in two functions. So first, here are my claims. OO is internal modular extensibility, and I will prove it by rebuilding OO from these first principles on top of pure functional programming. I will find that classes, mutation, and even objects are not fundamental to OO. And the key ignored semantic notion to understanding objects is what I call conflation. More on that later. The most fundamental kind of inheritance is Mixin inheritance, but it's not the most modular kind of inheritance. And the best kind of inheritance is, of course, to combine single and multiple inheritance. What O is not about, many people have ideas, incorrect ideas, on what is necessary or sufficient to be OO. I don't have time now for full debunking. Read the paper. What O is about, modularity, is the ability for developers to contribute to a software project while knowing as little as possible about the rest of the software. We need to focus on this part, know little about the rest, and that's enough. That's modularity. Extensibility is the ability for the same programmer to contribute to the software while specifying as little knowledge as possible given the existing software. And language internal means that those entities that are modular and extensible will be inside the language. More on that in a minute. And what is OO for? The purpose is to support division of labor. That is, I want to be able to have a large software and divide it in smaller parts, smaller tasks that people with small brains can address in a finite time. That's why it's not for your professor who's a genius, but for you, most of you, it is useful. For me, it is useful.
It's just fun.
For most of us, it's useful. The mechanism that characterizes OO is called inheritance. If there is inheritance, it's OO. If there isn't, it's not OO. Sorry, William Coop, you're wrong. What do I mean by internal versus external? You all are familiar with the notion of first class and second class. A first class entity is one that is manipulated at runtime by your programming language semantics as values. And sometimes you have to import them using reflection from things that are not usually available at runtime. Second class means it's processed by your language processor, part of its semantics, but it's all eliminated at compile time. Your static types, your macros typically do not exist at runtime. I will add two things that I dub third class and fourth class. Third class means this entity or concept does not exist in your language semantics, but there exists some tooling, some preprocessor called cfront or whatever, or some editor macro or some linker, something outside your language that handles this aspect. And the fourth class entity is one where it's automated in wetware, in your brain. You as a human will follow the design pattern, and if you follow the recipe, the informal recipe correctly, you can express this concept that is not directly expressible in your language. So for OO, I want these things to be first class, second class, internal to your language. Otherwise, anything is O. You can always apply the O as design patterns, but that doesn't count. Okay, so now I will want to have a minimal formal semantics of OO as first class entities. Why? Why? Because first, you only understand something if you can implement it. The Knut says it, so authority, believe him. And you could say some languages have OO as second class, but even the second class semantics is first class for whoever has to implement it. And if you're not the one implementing it, you're not the one really understanding it. So if you want to understand OO, you want it as first class semantics. And I want my model to be minimal, because otherwise it means you're still confused, you still haven't teased apart all the concepts, you're still mixing things, so it has to be minimal. Okay, so let's start with just extensibility. Like, forget about modularity for now. Extensibility is simpler. We have at runtime some values of some type V, and then we want to express extensions. What's an extension? Something that takes an old value that we can call, say, inherited or super, and it returns a new value that we call extended, and that's called an extension. If your type is a record, you can have a point that, let me this syntax for now, is a record that binds x to 2 and y. Oh, do I have a pointer? I do not have a pointer. Okay. And y to 4. And let me define an extension called paint blue that takes a value p and extends it as a record to have the symbol color bound to the value blue. So you can all imagine what applying paint blue to point p does. The point here is to give you an idea of the kind of things we do. It's not supposed to be complex, it's supposed to be very simple and familiar. Okay, so what can you do with extensions? Obviously, you can apply an extension to a value, that's the whole point of it, but you can do something even better. You can compose extensions, and then instead of having just a set of disparate extensions, now you have an algebra of extensions, and it's a monoid and more things. It's great. And the difference between the two is very important. If your extension language is supposed to be used, supposed to be very restricted and used as a second class, because then if your language actually allows composition in the language, it will be much richer than if it only allows applying. Okay. So how do I get from an extension to a value? Sooner or later, I have to apply it to something. And the right or intuitive thing to do is to apply it to a top value. A top value is a value that has minimal knowledge in it. So if your type is record, your top value will be the empty record. If your type is number, your top value will be 0. If your type is pointers between cells, your top value will be null or the equivalent, a unit type. And of course, if you are a pure, lazy, functional programmer with partial functions, your universal top value for all types is a lazy bottom. It works in any context, you can pass it along, but if you try to look into it, boom, it explodes, it aborts. You can say, hey, I know, I have functions from V to V, I want a V, I will use a Y combinator, a fixed point combinator. But yeah, if it works with lazy bottom, it will work with fixed point combinator. The fixed point combinator is the wrong thing here. It breaks the abstraction of going from an empty information and going all the way to all the information you need. So yes, close but no cigar. Okay, modularity. Before we talk of modularity, let's introduce records. You have values or various types. You have identifiers, or in this case, I will use symbols for my identifier type. And you have sets of bindings, also known as records or index products, which is basically functions that takes as input one identifier of whatever type it is, in my case symbols, and return the value of the proper type for that identifier. Example, my schema of record types is for X I want a number, for Y I want a number, for color I want a symbol, and I can define a point Q that is a record that binds X to 3, Y to 4, and color to blue. That works. That's the kind of things we want to do. So these records, no extensibility so far, no modularity so far, it's just a record. Okay. So what do we want, what do we call modularity? Modularity is the ability to define some value given things in a context. So let's say you have a context pi m, which for a set of known identifiers gives you a library object of the proper type. A modular specification for an object of type x is basically a function from pi m to x. Example, you have a library that gives you a function ls that lists files in the directory, so it takes a string as input and gives you a list of strings as output. You have a function sort that takes a list of strings and returns a sorted list of strings. And you can have a modular definition for, say, ls sorted that takes the modular context as input and extracts the sort and ls function from this modular context and composes them. So this is the kind of thing we do. It's just modular, so function from pi m to x. Easy. Okay. Now what if we want to define not just one value, but a module? What is a module? It's a binding that's for each of many identifiers, you return a value. We already have a context. We already have a concept for that. It's a record. So basically, defining a module in a modular way is taking a module context pi m as input and outputting a module body pi x as output. Pi m, the input, is the identifiers you can reference, and pi x, the output, is the identifiers you define. And you have now a modular specification for your pi x based on your context pi m. Okay. So that was, say, open specifications. Now, let's have a class specification. Now, every identifier I reference, I want to have a modular specification for. So I want to define them. So now I have a pi m to pi m. How do I extract the value? So I have a specification for pi m from pi m, but how do I get the thing? How do I link the thing? So at the low level, with C file, you have a linker that does that. It links the references. And with functional programming, we have something called the fixed point combinator Y that does exactly that. It closes the loops, it ties the knots, and it makes the reference back to the definitions. It does the right thing. The fixed point combinator was the wrong answer for extensibility, but it's exactly what the doctor ordered for modularity. Okay, small digression. You see your scheme. You say, oh, I know I will implement my fixed point combinator with pure applicative functions. It works, but it sucks because it only works like functions, okay? But it also does not converge when it should. And even when it does converge, it will recompute everything exponentially many times because it has no notion of sharing. The solution is to use stateful Y combinator. That's what letreg gives you in Scheme. Or to give you the lazy Y combinator. That's what letreg gives you in Nix. Or use second class Y combinators, but we're interested in first class, so let us discuss that. Other issue with functional programming in Scheme or Racket is that unary functions, which is what you use in functional programming, are very syntax heavy. And you can cope lots of extra parentheses. You can have the standard Scheme way or Racket ways to have make sure every function is called with proper number of arguments you defined it with. That's multipolarities with care. Or you can do like in ML, have autocurry. You define your function with a syntax that will do the right thing. If I have too few arguments, I will have a partial function. If I have too many arguments, well, I will apply the result to more arguments. So for my coup.racket library, I chose to use the stateful letreg from Racket and autocurry set of macros in a few tens of lines that do the right thing. Okay, so now let's put all these things together. We have functional programming, we have extensibility first class, modularity first class. How do we put that together? We have extensions that are functions from, say, some x to x. We have a modularity context pi m. Now we want an open modular extensible spec. That is, for each x that we want to define, I'm not going to define the x itself. I'm going to define an extension that I can later compose with other extensions. Only at the end, I want to apply it to a top value. So when I have a closed modular extensible spec, what I have is a pi m to pi of m to m. That is, for each value that I'm interested in using, I'm not defining the value, I'm defining modularly an extension of this value. So how do I resolve that? Well, for each value, I will want to apply it to top, and then I will have a pi m to pi m, and then I can use a Y combinator. That just works. Let's write that in Racket. We have a function instantiate spec, a Racket with autocurry. I have instantiate spec, which is just calling the Y combinator on something that for each I applies a spec to mi and the top thing. And of course, I can compose my specs. And that means I have this inherit function to compose my modular extensible first-class specs. And what it does is just compose each of those functions inside the spec. These are the same two functions that I showed in the first slide. And this thing has got a name. It's called the Mixin inheritance. It's been described formally by Braha and Cook in 1990. It just works. It's all the OO you need, and some languages actually implement that this way. So how do I use it? I have my type spec, which is a function from the context to the identifier to the super thing method that you inherit from, and that returns the extended thing. So every spec you write will take 3 arguments called self, that's the typical name for this extensible context. You have a second argument, method ID, or I will use just I in the following slides because otherwise it doesn't fit in the slide. But the name of the method ID. And then an argument super, which is the value that you inherit from that you're going to extend. You can refactor by changing the order of arguments. That doesn't matter. Have it your way. So can we implement the famous cohort point example of every OO paper? Yes. So let's define first a cohort spec, which is a spec that given self, I, and super, if the method name ID I is X, it returns 2. If it's Y, it returns 4. Otherwise, I pass the super unchanged. That defines basically the specification for a record that has X2, Y4. You can have similarly a color spec that binds color to blue. And I can then define a point that instantiates the spec obtained by combining those 2 specs. I can print what is the value X of point P, it's 2, and the color of it, it's blue. That's trivial. It's especially trivial since all these definitions have constant values for the slots, and the slots don't even conflict between the 2 definitions. You could even change their order. Let's have now an example that is less trivial. So let's have 2 examples. The first is a spec that exercises extensibility. It takes an extra argument dx, and if you ask the x value for your object, it will add dx to the inherited super value for x. Otherwise, do nothing. And the row spec, it computes the radius of your point in polar coordinates. So you have a point in rectangular coordinates x and y. And so this exercises not the extensibility, but the modularity aspect of the system. It will extract from the modularity context x and y. It will sum their squares, extract the square root. It applies the formula, it just works. So now let's apply it. We can construct a point R that instantiates the spec obtained by combining the 3 specs above. So if I ask the value x, it goes from right to left. So it says, hey, row, do you have x? No. That's OK, no problem. Hey, cohort spec, do you have x? Yes. Oh, yes, it says 2. And then it asks to add x spec 1. Yes, but I'm going to add 1 to it. So the way that works is that x will be 3. And row then will compute row from x and y, and it's x and y from the whole thing, so x will be 3, y will be 4, apply the formula, it's 5, it just works. What have we done? What we have done is that we have reconstructed recognizable OO from first principles, which said, OO, we want to combine modularity and extensibility in a minimal way as first-class entities, and we found exactly up to isomorphism what Braha and Cook defined in 1990, what Nix uses since 2015. Exactly the same thing, OO in 2 short definitions that apply in any functional programming language. We have no classes, no mutation, no objects. What? There are precedents. ELT scheme in 1982 did exactly that for its object system. They did not have the theory of it, but they had the complete system with windows, etc., using this for their object. There are schemes that also had mutation, but they didn't really use mutation for their objects, they just use fixed points. The object system of ELT scheme was published as a library in 1992 by Ken Dickey. Braha and Cook in 1990 had a theory of this mixed inheritance. They didn't have any useful implementation, but they had all the theory. If any of you has ever used Google, a small company have heard of, all of Google services are configured using the Google configuration language. It uses exactly this object model. It's a lazy functional programming language. It just has dynamic scoping. Anyway, people 10 years later wrote Jsonnet, which is basically a cleanup of a DCL with lexical scoping. And interestingly, since 2015, if you have ever used Nix OS or Nix, it's a package system where you can build all of Linux, or you can also work on Mac or in Windows in your WSL. All those thousands of software packages are configured using this pure, lazy, dynamic functional language in which OO is implemented with two functions, just isomorphic to those I showed, and it's also isomorphic to Jsonnet. It just works. Wow, so I'm not just making it up. It already exists for a long time. All I'm making it up is maybe simplifying it or showing the simple version. So you may have noticed that in ELT scheme, there are no objects. In the ELT scheme documentation, where this call object is any old value. Oh, it's a scheme object, a Lisp object, whatever. They call instance a record that was obtained through a fixed point. But it's just any other record. You could obtain it in a different way. It's not a separate type of values. They call component, whereas I call a specification. And a component is not an object. You can't extract you can't compute a method from a component. You first would need to instantiate it, if you could. And this is in contrast with other, what I call prototype object-oriented language, such as DCL, Jsonnet, and Nix, that do have objects. So what do they call object if there's no object in ELT scheme? What is an object in those prototype object languages? It is the conflation of a spec and its target. Conflation means just it's a hidden product. Implicitly, there's a product. And there's also an implicit cast. Magically, depending on the context, I will cast my product to its left or right component. So I will call prototype the conflation of a spec and its target. The target is just the lazily resolved fixed point of the spec. So if you want to compute a method on your object, oh, this object is a prototype, let's compute the method. We just drop the spec, we keep only the target. We ask what the value of the method is. Or you want to inherit from a prototype. No problem, let's drop the target, take the two specs, use the inherit function, and then tuck in the target as a lazy fixed point if you need it later. So that's a model that exists since as old as OO itself. Like Annie in 76 had essentially that, SingLab 77, South 86, although there are lots of mutation everywhere to confuse the point. The most famous and most popular language in the world is JavaScript. Since 1995, it uses prototype object orientation. They also added classes in 2015, but at heart, it's still prototype objects. DCL, Jsonnet, and Nix are already discussed. So, wow, this is prototypes, this is objects. What about my favorite OO feature? Everyone's favorite or least favorite OO feature is classes. What is a class? A class is just a prototype for a type and associated methods. In class OO, what you call the object is not your spec times target, it's an element of the type that is the target of your spec. Now, what you call a static method in OO, in class OO, is just a method of the target type for your element. And when you call an object method in class OO, it's just calling one of these static methods with the element as the first argument. Most people who do class OO have no notion of spec and target, and yet, they call abstract class a class that you will only use for its spec, and they call concrete class a class that you will only use for its target. So they don't have explicit notion of spec and target, and yet, implicitly it's there. And if you don't believe me that class OO is just pure lazy functional programming with prototype OO at compile time, well, just try program with C++ templates. It's exactly that. What about objects? Well, we saw that in T, an object doesn't have a meaning, really. In prototype object, an object is a spec times target. In class OO, an object is an element of the type that is in your target. So the word object does not have any uniform meaning in OO. And since you can have OO without object, it's not even a necessary concept for OO. So object orientation, despite the fact of having object in its name, does not have object as an essential fundamental concept. And that's okay, that's normal, because fields are named when you need to demarcate them from other fields long before they're understood, if they are ever understood. So most fields of knowledge are total misnomers. Computer science is not about computers. You should be aware. Yeah, that's okay. No time to discuss types in detail, but I will just say this, that subtyping is very important if you want to add types for OO, but subtyping does not commute with fixed point. So the subtyping relationships you have between your specs are not the subtyping relationships you have between the fixed point of your specs. And once you understand that, there are decades of confusion about subtyping and inheritance that disappear. Type classes or modules are just modularity without usually having extensibility. That's why they suck. You can do better. I've done better. The side effects, they are not necessary, but you can have them, and they can be very interesting, and then can also be very interesting, because mutation is hard, but it can also be very useful. Multiple despised method combinations, they fit in this model, but no time to discuss about that. And one thing don't have much time, but I still need to tell you a little bit about it, is single or multiple inheritance. We've seen that mixing inheritance is the most fundamental, just 2 lines of code. Singular inheritance, just a few more lines of code, but more concepts, and it's less expressive, but it's also more efficient. Multiple inheritance is just as expressive as mixing inheritance, but more modular. Why? Because with mixing inheritance, you must manually compose all those mixins in the right order with the right dependencies. And that means that the transitive dependencies of your mixins become part of its interface. Because if you want to use this mixin, you will have to use all these in the right order and linearize them in the thing. With a multiple inheritance, it's not part of your interface, it's taught automatically by the system. This is why multiple inheritance is just as expressive, but more modular than mixing inheritance. And of course, you can have both the performance of single inheritance when you need it, and the expressiveness and modularity of multiple inheritance when you need it. And Ruby, Scala, and Gerbil Scheme do that right. So it's possible. I hope that Racket will do that right too soon in its standard library. No time to discuss inheritance in the, okay. Let's redo the claims. OO is internal modular extensibility. I think I've proved it. Classes, mutation, and objects are not fundamental to OO. You can add them on top or do without them entirely. The key notion that simplifies all the semantics of OO when you have it, and without which everything is confusing, is this conflation of spec and target. Once you understand that, everything is so much simpler. Mixing inheritance is the most fundamental inheritance, but the best one is to combine single and multiple inheritance. This presentation was written with scoop.racket, a few hundred lines of code, so a pure functional OO. I care because when I was a kid, there was this great flame war on the Usenet with dysfunctional programmers versus object-tunable, disoriented programmers talking past each other. They still talk past each other and have been for decades. And yet, in the 70s, Lisp had OO and FP at the same time, and no one to claim they were opposite. And in the 2000s, Fortress and Scala showed you can have OO, FP, and types at the same time. So the opposition, if any, is in mind, not in reality. I have to skip the slide about that because I'm already over time. If you find yourself in a flame war, be humble, not be fanatic. Maybe you're just talking past each other because you have incommensurable paradigms. Read the article by Dick Gabriel about that. The solution is to go wider. Maybe there's a wider paradigm that can express the nuance you care about, the nuances they care about. That's very important and very useful, because if you are a young academic, you'll find that your professor has already picked all the low-hanging fruits from the paradigm he taught you. So if you want to follow their paradigm, you'll be a third-rate researcher. If you want to be a first-rate researcher, you have to adopt your own paradigm, for instance, by combining existing paradigms. And then you will find that to identify the concept that will make you famous, simplicity is very important. And for that, Racket is great because it has lambdas for semantics and macros for syntax. Thank you, I'm over time, sorry, apologize. Depending on the vagaries of success, I will be either looking for people to hire or people to hire me.
But you know,
contact me for collaboration. Thank you.
All right, I think we've got time for a question or two while our next speaker starts setting up.
How do you feel about OCaml's object system?
There's a reason why, how do I feel about OCaml's object system? Well, there's a reason like why most OCamlers do not use it. And that side, it's not received enough love. OCaml, the O stands for how much care they have for the objects. Last question.
Well, I'll tell you what, I'll take mine after lunch.
Thank you very much, Jason. And thank you everyone for having me.
Oh, sure.